Mathematics is often introduced as a cold theoretical discipline, a world of symbols on a chalkboard that can feel intentionally isolated from the physical world. Contrast that with the quilt frame. This is a space of tactile, domestic craft, where every choice is rooted in physical contact and shared tradition. In many classrooms, students jump straight to manipulating symbols on a page, often losing the sense of logic that those symbols were meant to represent. But we are naturally wired to understand complex relationships spatially. We grasp how shapes transform, rotate, and fit together through our hands long before we learn to describe them with algebra. Quilting serves as a bridge between these two worlds. It is an environment where the physical constraints of sewing turn abstract geometry into a visible, measurable reality. The logic begins with simple pieces, like half-square triangles. Arranging them into a quilt block invites immediate observation of how repetition and shape build a larger whole. When you rotate or reflect blocks to create a pattern, you are physically performing transformations and calculating fractional ratios. To turn a design physical, you must account for the seam allowance, the margin of extra fabric for stitches. Your cut width must equal your finished length plus twice the allowance. Forgetting this doesn't just change the side's length, it changes the entire geometry. Because you are building a two-dimensional shape, that small linear mistake causes the total area of the finished block to change quadratically. To make the pieces fit, the quilter is forced to solve these algebraic constraints before the first stitch is ever sewn. This specific quilt block is designed to represent a right triangle, with square regions built upon its two shorter sides. In this layout, the two tree-patterned squares are geometric representations of a squared and b squared. In a physical dissection proof, rearranging the fabric pieces from these two smaller squares should theoretically fill the square on the longest side. As the reassembled fabric shows, the pieces from the two legs perfectly cover the square on the hypotenuse, visually proving the relationship a squared plus b squared equals c squared. This maneuver takes an equation that is usually invisible and makes it entirely tactile. Does moving these specific scraps of fabric around actually prove the Pythagorean theorem for every possible triangle? No. A physical quilt only demonstrates one specific case. It shows us that the math works for this exact set of dimensions, but the quilt provides the intuition needed to ask the bigger question. It gives the mind a physical reference point before we turn to the chalkboard to find a solution that applies to all circles and triangles. To reach a universal truth, we eventually leave the fabric behind. We use general dissection and abstract algebra to show that this relationship holds no matter how much the proportions of the triangle change. The quilt offers a low floor, a way for anyone to begin by noticing and measuring physical pieces. The abstract formula provides the high ceiling, allowing us to generalize that intuition into a rigorous universal proof. The next time you see a quilt, look past the artistry. Notice the patterns, measure the relationships, and you'll find the mathematics stitched into the fabric.